Hello everyone, this is Matias from the Oxford Robotics Institute, and I will present you my work on how to make safer virtual teacher-rapid systems for legged robots. Virtual teacher-rapid systems are a practical way to deploy legged robots, or robots in general, in real-world scenarios. For example, here you can see how we deploy our Animal Bee robot in some industrial facilities, and the system was able to go from two different points and to track the whole trajectory just using vision. An advantage of these systems is that since we already know the trajectory because it was taught by an operator beforehand, we don't need actually a global planner to reach one point and the other, but only to track the whole trajectory. So in order to make the system safer, which is a really important thing for legged robots, since the way in which they move is actually way different to a wheel robot, because they can hit other things, or if the environment changes a little bit, if someone walks by, it is really important for the robot to be reactive to these sort of situations. So in order to enhance our system and to make it safer, we develop a safety layer for the systems, and you can see here. Basically, our system is based on our previous work, but now we're including local information, like the local representation of the environment given by an elevation map that is usually available in legged platforms. And we're processing this using pretty efficient operations that I will present next. And we're able to obtain some really rich representations that are used to create the safe policies that are processed by a Riemannian motion policies controller that we use now to provide the twist commands that are sent to the whole body controller in this case. This is in contrast to our previous approach, in which we only use some sort of blind controller that only received some position goals and just generated what was the velocity command in order to reach this one, assuming that the space was free. Our representations are the ones that I show here. For example, here we can observe a sign distance field that is like a classical representation for optimization-based motion planning. But in this case, we're just using this local information to obtain a local field that allows us to keep the robot in safe places. And we're able to compute this pretty efficiently since we're just considering that the world is like a 2D space. So we can just compute this in milliseconds. On the other hand, our other representation is this geodesic distance field that basically generates one sort of attractor that guides the robot to reach some specific goal, but in this same goes around the obstacles. So in this way, we're providing a more informative guidance for the robot to reach this specific goal, when it's complemented with the sign distance field, allow us to get safer, allow us to track the trajectory in a safer way. Here we can see some experiments that we did in the lab. So in this case, I'm showing one experiment that we did in some sort of obstacle course. So we put some obstacles, we taught a trajectory around these obstacles, and the robot was able to go back and forth, avoiding all these obstacles by the combination of all these fields that I presented before and using this RNP controller. For example, here what you can see, the color field, is the geodesic one, in which the yellow spot is a tractor that the robot has in this specific moment and is trying to reach when following the trajectory. We also did some longer and more complicated experiment around a lab. So the robot had to walk through pretty narrow passage and also go through some doors and other kind of objects that were available in the lab, and so also able to go without hitting anything, just by exploiting this local representation and the global trajectory that was previously taught by the operator. So in this work, I presented how to make our virtual teacher safer by exploiting these efficient representations of the environment. The challenges now are to make the system faster, because now the trajectories are tracked really slowly, so we want to be able to repeat the trajectories faster, but keeping the system safe in order to make the system more useful for real-world applications. So if you have more questions, please don't hesitate to reach out in the email that you can see here. Thank you very much.